All right, so this is our first problem of many that we'll be looking at. Um, it's what's called a fundamental problem in your textbook. And what you need to know about all the fundamental problems is that in the back of your textbook, there is sort of a skeleton of a solution. Now, of course, I'm going to provide a good solution to you here. So I don't know at this point if you're seeing this because we're not having regular class or if we are having regular class. For having regular class, I'll suggest to you during class that you um, try to use the skeleton solution before you come here to get the video solution to them. All right. Um, and these fundamental problems are always problems that we're going to do in class together, although we won't necessarily get to all of them, but then you could refer to these videos as you need help. So the first thing that we've got to learn in statics is how to deal with vectors. Okay. So right now you're going to be getting a double dose. We're going to talk a lot about vectors in here in statics. And of course, most of you, if not all, are enrolled in Calc 3. So you're going to see a lot of the same things twice. Okay. But that usually works out pretty well. And nobody seems to mind that too much because you get to see two slightly different perspectives on the same material. And of course, there's a little bit of overlap with things like homework problems to help you get the hang of it. Okay. So in this particular problem, what we're looking at is we got this bolt and then there's two ropes coming off of the side of it. And it says there, determine the magnitude of the resultant force. So let's just sort of take that thing apart real quick. So, first of all, the resultant force. This could also be called the net force, N-E-T, the net force, but basically it means the total. Okay, so it's resultant. You see the word result right there. So, what's the result of these two forces that are pulling? The other thing I want to point out to you is the word magnitude. Okay, so with a vector, as you may already know, there is both an amount and a direction. Okay. So in physics, we might say you're going 60 miles an hour east. So there's an amount, 60 miles an hour, and there's a direction east. What we're going to do, we're going to represent the efforts of these two ropes with force vectors. So let me call this guy vector B. And this guy, vector A. Okay. Now, those vectors then have a length. B is 2 kilonewtons, which is 2,000 newtons. A is 6,000 newtons or 6 kilonewtons. Okay. And they both have a direction. B is just sort of south, so to speak. It's down there in quadrant 4 at 45 degrees. And A is in quadrant 3 down there 60 degrees below the horizontal. Okay. So what we have to do is we got to put these things together. Okay. So what tends to be in these first set of problems, what tends to be the most tricky parts, the most difficult parts perhaps, is just working out the geometry, getting your angles and all that sort of thing. And I know that all of you have had trigonometry, but people usually tend to think of trigonometry as something that medieval monks used to do for fun or whatever, and nobody cares anymore. But you need to get all that trigonometry back into your head. Okay, sines, cosines, tangents, how the inverses work, side angle side, maybe SOHCAHTOA or something like that. Get all that information into your head. Now, some additional things that we're going to be using specifically in this first few set of videos is law of cosines and law of sines. Okay. And most students don't have a lot of experience with those, but they're super easy to use. and you're going to get the hang of it really quick. Okay. So in order to figure out how these two vectors work, kind of what you need to do in your mind is you need to think about them as directions. So for example, we might say, let's walk this way a certain distance, and then maybe that distance is 6. All right. And then we're going to walk another way a distance of 2. And my total path from start to finish is my resultant. Okay, so to do things generically, then this side of the vector is of my triangle is A, and this side is B. Okay, now when you're doing vector notation, you always want to put a little arrow over the top of them to signify that you're talking about the actual vector itself. So the magnitude as well as the direction. If you just, like if I just put R, which is what I did originally, that means the magnitude of it. Okay, so we'll do that when we need to. Okay, so let me clean things up just a little bit here. I'm going to get rid of this 6 and get rid of the 2. And I'm going to see if I can make my triangle a little bit bigger here. Except I deleted part of my arrow there. That wasn't cool. There we go. I'm out of control. Okay, now, when it comes down to working out the geometry, what I like to do is, well, I've got A, B, and R. It's kind of like A, B, and C. I'm going to label this angle beta, and I'm going to label this angle gamma, and this one I'm going to call alpha. Okay, so I've got my angles alpha, beta, and gamma. Sorry that alpha didn't show up too well. Let's do that in black. Okay, so I use the Greek letters there, alpha, beta, and gamma, to represent how those are going to go. Now, the reason that I like to do it that way is because whenever I'm dealing with the law of sines, then if I've got my angles labeled that way, it's really easy to say that side C over the sine of gamma is equal to side B over the sine of beta, and that's equal to A over the sine of alpha. Okay. Now, in our particular case, we don't have a C, we have an R, but you see the pattern there. It's the opposite length over that angle, opposite length over that angle, opposite length over that angle. And those things all make a really nice ratio that's very useful. Okay. But what we have to work out is our angles. Okay. So that can be where the geometry can get a little bit, a little bit weird. Not sure what I did there. Okay, so I'm going to zoom in quite a bit. So let's think about vector A. For vector A, we know that this angle right here is 60 degrees. Okay, at this point, we don't know what beta is. Okay, we don't know what alpha is. Okay, but we know that's 60 degrees. So what's useful about the 60-degree information is that if I put another horizontal line here, this guy is 60 degrees, like that. Okay. And now let's think about what's happening with vector alpha. Okay, vector alpha is 45 degrees down from the horizontal, which means that this angle right here is 45 degrees. Right there. Okay. And so you can see that gamma turns out to be the 60-degree angle plus that 45 degrees, which is 105. Okay. So I've got gamma. All right. Now, I don't know beta and I don't know alpha. Okay. And truth be told, at this point right here, we don't actually have any way of finding beta or alpha because we don't know r. We don't know that long side. All right. So law of sines is actually not a great way to go here because we've run into a wall. All right. Now, you're going to run into walls a lot. What do you do when you run into a wall? Well, you find another way to go. Okay. So in our case, the other way to go is instead of using the law of sines, we'll use the law of cosines. The law of cosines says that c squared is equal to a squared plus b squared minus 2ab cosine theta. All right. So what does cosine theta refer to? Theta in this case is always going to be whatever angle is opposite of C. Okay. So imagine if it were 90 degrees. So if we had a right triangle, let me draw a right triangle over here. Boom, boom, boom. Okay. So if this is side C here, so I've got A and B, okay, you can see right away cosine of 90 degrees is 0. And so what I get back is just Pythagorean theorem. Okay. So that works out. So the 2ab cosine theta term actually is a way to adjust the Pythagorean theorem to fit a non-right triangle. All right. Now, in Calc 3, when you get to something called dot products, you'll actually figure out a way to prove the law of cosines, and it's pretty cool. It's I think you'll like that when you get to that. Now, in our context, what are we dealing with? Okay. Well, what we're dealing with is this. R squared is equal to a squared plus b squared minus 2ab cosine gamma. All right. Because what we're interested in is the length of r. The angle opposite of r is what we called gamma, even though I wrote down an alpha. There we go. That's better. Okay. And so we put some numbers in there. A has a value of 6. B has a value of 2. Minus 2, 6 times 2 times the cosine. What do we say? That was 105. 105. Just like that. Okay, so that's what r squared is. Okay. Now, you can work all that out. Type that into your calculator. Boom, boom, boom. Take the square root of everything. And what you're going to get is that it is, what does that turn out to be? Turns out to be 6.798. Okay, just like that. Now that's far too many sig figures. What I like to do is to keep track of one extra digit. Okay, we only need to report 3 digits, 3 sig figs. So like in your homework, you would enter 6. That's going to round up to 6.80. Okay. But in all your calculations, if you use 6.798 going forward, everything's going to work out just fine. Okay. Some of you are going to have an impulse to do something like this: 6.798231495. Nobody cares. Don't do that. It just makes you look, it makes you look a little silly. Okay. Don't do that. If that's meters, if we're talking, let's say this was meters, 6.78 meters, then that right there, already the 8 is at the millimeter level. That's a millimeter. This is a micron. That size right there is the thickness of a hair. So you end up just looking kind of silly if you think you can specify the length of something to the same size as a red blood cell or something like that. So don't do that. Just break yourself of that habit, okay? I don't want you to look silly. So let me erase this. We don't want to look silly. And we've got the magnitude of our vector. But it also says its direction measured clockwise from the x-axis. Okay, so let me scoot around over here just a little bit. The direction measured clockwise from the x-axis, which means we need this right there. So let me call that theta r. There's theta r for us. So how are we going to find theta r? Well, one of the things that we can realize right away is that if we take that 60-degree angle and we add to it beta and theta r, it should be 180 degrees. And what that's going to do for us then is to say that theta r, the angle we're looking for, is really 180 minus 60 minus beta. So if we get beta, then we can get this thing. All right. Now, to get beta, that's where we're going to go back up and take a look at the law of sines. That's going to help us out there. Okay. So let me pick a good spot to work on here. So what I got is I'm going to have r over the sine of gamma has to be equal to b over the sine of beta. Okay, so if we do a little bit of algebra on that, what we're going to find is we're going to say that beta is the inverse sine. Now I'm doing several algebra steps in one. Okay, don't do this. I'm just trying to save a little bit of time. On your paper, you go through it one step at a time. That's actually very important. And normally I will do that for you, but this video is getting kind of long and I'm starting to run out of working space here. So I'm trying to compress a little bit. So I'm going to cheat a little bit. Do as I do, not as I say. Okay. But I got the inverse sine there. Sine goes over there. I'm going to have b over r times the sine of gamma. Okay. Now, once you plug in all of your numbers, so you know b is equal to 2, r, we just found that, use that 6.798 number. Gamma, we know that's our 105-degree angle. We've used that before. Plug all those numbers in, and what you're going to get is that beta is 16.51 degrees. Okay. So take that number, plug it in for beta, and what you're going to get then for theta r is 103.5 degrees. Okay, just like that, 103.5 degrees. Don't round it to 104 in this case, because actually putting it at 0.5 rounds it. It's actually like 103.49. And so that actually rounds down to 103, depending on how you want to do things. So we can talk about more of those sorts of things later. But there we go. We got the magnitude. We ended up getting that magnitude by using the law of cosines. And then we got the angle. To get the angle, we had to fall back into the law of sines to pull that off. The The thing to be careful about is your geometry. Work out your angles very carefully. It's worth taking your time. Make several drawings if you need to. It's super important to make a good drawing, okay? That helps your brain. It frees your brain up to problem solve. The number one thing that students do wrong when they start working problems is they don't make a picture. You gotta make a picture. It helps your brain work better. Okay?